Okay, so the following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. Okay, so today we're going to take a look at section 9.3, but before we do, I had a couple of requests from a student from 9.2. So we'll take a look at that. This is again, from section 9.2, and this is number 37. The directions say simplify the expression, and then it goes on to say the variable represents a positive real number. And we have the following. We have t to the 6/5 power multiplied by t to the 9/5 plus t to the negative 6/5. All right, so we're going to start out by distributing. And we're going to take t to the 6/5 times t to the 9/5. So t to the 6/5 times t to the 9/5. And then plus t to the 6/5 times t to the negative 6/5. All right, so let's take a look at this first product. Multiplying two powers with the same base, they both have the same base of t, we add the exponents. 6/5 plus 9/5 would be 15/5, which would be 3. So we get t cubed. Then the next product, again, multiplying two powers with the same base, t to the 6/5 times t to the negative 6/5 would be t to the 0, which is 1. So final answer, t cubed plus 1. Any questions about that one? All right, we've got one more. This is from 9.2 also, number 38. It says simplify the expression. If the expression is not a real number, enter not real. And we have 1 over 1,000 to the negative 7/3 power. So that would become 1,000 over 1 to the positive 7/3 power, or just 1,000 to the 7/3 power. But we could write that as 1,000 to the 1/3 power and then to the 7th power. Well, the cube root of 1,000 is 10. So then we'd get 10 to the 7th power, which would be, let's see here. I got the right number of zeros, 5, 6, 7. That. Now, the student that asked about this, you actually had the right number of zeros, but you put a comma there. And so the WebAssign was confused because the commas should have gone here and here, not there. So you did everything correctly except the placement of that comma. All right, that's all the requests that came in. So now we're going to go on and take a look at section 9.3. A few rules I want to look at. Question?
Yeah, so I got one from the homework from a couple days ago.
Okay. You want to tell me, or you want me to pull it up and look at it?
I can tell you. Square root of 510.
Okay, square root of 510. That's it?
Yep.
Okay, and it says simplify.
Yeah, take it to the 4th decimal point.
Oh, okay, so it's a calculator problem.
Yeah, but anything I enter, I just get 510 back.
Okay, so what kind of calculator do you have?
The TI-30XS from Texas Instruments.
Okay, so you've got the same one I've got here.
Yep.
Okay, so what you need to do, first of all, the square root is a second function, so you're going to push the second function key, okay? Then you're going to push the button that says x squared, and what that's going to do, it's going to access the square root button.
Right.
So right now on your calculator, you should have this, a square root with a left-hand parentheses.
See, mine doesn't pop up with a parenthesis, so just add that in.
Okay, is what you're seeing, is it this? Is there a little X in the index?
No.
Okay. Okay. Hang on. Actually, let me see the top of the calculator. I want to see what it says in terms of the, okay. Got it. Yours is not the same as mine. It's slightly different. Not a big deal, just now that I know. So when you access this, you get this thing, right?
Yeah.
Okay, so what you need to do now is basically put 510 inside that box.
Right.
And then push equals.
Yeah, see, it works for everything else except for this, because that's
Okay.
all I get back is 510.
Oh, okay. Hang on. I am going to stop the recording for just a minute, or pause it rather. Okay. So, hang on. You got, tell me what you got. You got 2 point, go on from there.
2.25831.
1, okay. And then what's after that?
7958
Okay.
times 10 to the first.
Okay, all right. So basically it's giving you your answer in scientific notation.
Mm.
So if you wrote this as a regular number, it would be 22.58317958, because multiplying it by 10 to the 1 would move the decimal point over.
Right.
Okay. So, and it said to 4 decimal places.
Yes.
So that would be here. The 7 would round up. So 22.5832. I want to try one more thing with you. So I'm going to actually pause the recording one more time. Again, all right, so we got that figured out. If any of you watching this video have issues with your calculator settings, let me know and we'll work it out with you. Okay, so was there any other questions, Russ?
Nope.
All righty, then we're going to go ahead and go on to section 9.3. And I want to sort of establish some things that you may or may not have noticed. If we take the square root of 3 squared, what do we get? Square root of 3 squared. We get 3, right? How about the 4th root of 7 to the 4th power? We get 7. How about the 12th root of 5,318.2 to the 12th power? We get 5,318.2, right? So in general, the nth root of a to the n equals a if a is greater than or equal to 0. In other words, if the base is positive and we're taking the same root as the power, they undo each other, because basically what you've got is this. Does that make sense? All right, so we're going to take that and put it in our bag of tricks or whatever to use here in a bit. Now, we're going to look at a couple of rules. They are not new rules, but they are new in that they are in radical form instead of exponential form. All right, so back in section 9.2 that I referred to the other day, we have a rule that says a product raised to a power, you attach the outside exponent to each factor inside. So for instance, 3x to the 4th power is 3 to the 4th power, x to the 4th power, which then becomes 81x to the 4th power. Okay? You all right with that? Now, let's say we have ab to the 1 over n power. Again, it's to a power. This would be a to the 1 over n power times b to the 1 over n power, right? Same idea. Let's take that statement and let's write it in radical notation. That would be the nth root of the product AB equals the nth root of A times the nth root of b. So what that allows us to do, and we actually did some problems using this rule before, but I just kind of brushed over them knowing what was coming. Let's say I've got the square root of 9x to the 4th. Okay, that's equal to the square root of 9 times the square root of x to the 4th, which is 3x squared. You okay with that? So if I've got a product inside a radical, I can deal with each factor separately, taking the whatever root it is of the whole thing. Okay, so let's apply that to some problems. Let's say I have the square root of 28. Now, the directions say this. It says simplify each expression. The final answer, I'm going to tell you ahead of time, the final answer is 2 square roots of 7. Now, does that look simpler than that? Not really. So maybe we need to define what we mean by simplify the radical. This goes back to the old days where you had monks in a monastery with a quill pen and some parchment paper, and they didn't have scientific calculators. They probably didn't even have an abacus. And so the idea of simplifying a radical was getting everything outside of the radical that we can first. Okay, now, if I take the square root of 28 and I factor it as the square root of 4 times 7, I can then separate it into 2 radicals, the square root of 4 times the square root of 7, using that rule we just talked about here, this whole thing, okay? But now I can come back and say, well, the square root of 4 is 2, so I get 2 square roots of 7. So that's how I got from here to here. This is considered simplified because what's left inside is not a perfect square. It doesn't have a factor that's a perfect square other than a 1, which doesn't get us anywhere. So I've simplified it as much as I can. That's called simplifying the radical. Okay. Now, if you punched this into your calculator, you'd get the same answer as if you punch that in, you get some decimal answer. But this is simplifying the radical. So what we're doing, we're taking the radicand and factoring it into factors that are perfect squares and other things, we'll say leftovers, because we can then unsquare the perfect squares, kicking the base outside and thus simplifying the radical. Okay, let's take a look at another example. Let's say I've got 9 times the square root of 54. The 9 is already outside. We don't have to do anything with it yet. 54 is 9 times 6. Well, 9 is a perfect square. So if I broke it down like this, I could then break it down further like this. And I could say the square root of 9 is 3. So I've got 9 times 3 times the square root of 6, or 27 square roots of 6. Now, why didn't I break the 6 down further? Because it breaks down to 2 times 3, neither of which is a perfect square. Okay. Now, let's see here. 54 could also be written as 2 times 27. So why not break it down like this? Well, because 2 isn't a perfect square and 27 isn't a perfect square. So the goal is to factor it with perfect squares and then leftovers. Okay. What if I don't happen to know that 9 is a factor of 54 and 9 is a perfect square? Here's the long way. This is like the deer in the headlights. I don't know what to do. Okay. We're going to do the prime factorization of 54. We're going to break it down into primes. 2 times 27, 2 times 3 times 9, 2 times 3 times 3 times 3. Okay, you okay with what I did there? Well, this, whoops, could be written as 3 squared. Oh, there's a perfect square. That's the 9 that I had before. So I can go 9 times 2 times 3 times 3 squared. Oh, well, that's not a perfect square. Can't do anything with it. That's not a perfect square. Can't do anything with it. That's a perfect square. okay? The square root of 3 squared would be 3 on the outside, and then we've got the square root of 6 left over, so 27 square roots of 6. That's sort of a longer way to go, get you the same place, but if you can't just immediately see that, oh, there's a square and some leftovers, you can always break it down and then build it back up, creating squares or whatever it is you need. All right? Good to go? Okay. Now, what about this? I want to simplify the cube root of 40. Well, I'm no longer taking a square root, so I'm not looking for perfect square factors. I'm looking for perfect cube factors. 40 is 2 times 20, which is 2 times 2 times 10, which is 2 times 2 times 2 times 5, which is 8 times 5. Or tell you what, let's just leave it as 2 cubed times 5. So the cube root of 2 cubed times 5. Ah, I've got a cube and leftovers. Now, I skipped a step on the last problem, okay? So I could do this, and then this would become what, a 2 outside, so you'd have 2 cube roots of 5. You seeing that? No? Okay. All right, let's back up. Are you okay how I got there? All right, so here we have the nth root of a to the n, the cube root of 2 cubed, so that becomes a 2 outside. And then we still got the third root of 5 left. You okay with that? All right, now I'm going to go back and do what I did on the last problem, but I jumped ahead too soon. Rather than breaking this up, what I can do that's less work is I can just go through and take it factor by factor. The cube root of 2 cubed is 2 outside. The cube root of 5 can't do anything. So there's my answer. So rather than literally writing each separate factor to some index, I just cross them off as I go along. Does that make sense? Okay, all right. Here we have the 4th root of 32. So I'm looking for something raised to the 4th power inside the radical. 32 is 2 times 16, which is 2 times 2 times 8, which is 2 times 2 times 2 times 4, which is 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power. Okay. But I'm going to write it as 2 to the 4th times 2 to the 1 power. Why am I going to do that? Because I want 4th powers inside so that I can take the 4th root. So this becomes 2 outside. The 4th root of 2 to the 4th power is 2 on the outside. And I still got the 4th root of 2 left inside. There's the takeout and the leftovers. Okay. Question? Nope. Okay. All right. Let's see here. Simplify each radical expression. All variables represent positive real numbers. So in other words, we don't have to worry about absolute value bars. We can assume that all the variables are positive. And this says the square root of 50x squared. So what I need are squares and leftovers. 50 is 2 times 25, which is 2 times 5 squared, right? So I could write this as 2 times 5 squared times x squared. Okay? So the square root of 2, not going anywhere. The square root of 5 squared would give me a 5 on the outside. The square root of x squared would give me an x on the outside, and I've got the square root of 2 left over. So 5x square roots of 2 would be the final answer. Okay. Square root of 75, b to the 8th, c. 75 is 3 times 25. 25 is a perfect square, right? So I could write it as 5 squared or leave it as 25, either way. So I've got what, 3 times 25 times b squared times b squared times b squared times b squared times c. Why did I do that? Well, b to the 8th power, I could write it as a square times a square times a square times a square. Don't panic. There's an easier way, but I'm getting there. Okay. So now this isn't going anywhere. This would be a 5 outside. This would be a b 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 outside. And I've got the square root of 3c left inside. So I've got 5b to the 4th square root of 3c. Okay. Now, that seems a bit ridiculous to do it that way, and I think it is, but I wanted to start there. Let's just take a look at the square root of b to the 8th power. Actually, you know what? Wait, let's do this instead. Let's do the square root of b squared. Well, that's just what? B, right? What's the square root of b to the 4th power? That's b squared. What's the square root of b to the 6th power? That's b to the 3rd. What's the square root of b to the 8th power? That's b to the 4th, right? So if my exponent is a multiple of my index, I can just pull it out that way, right? Without having to break it down into squares. So going back, what I could do is this. I could say, okay, this is 3 times 25 times b to the 8th times c. That's not going to go anywhere. That's going to give me a 5 outside. That's going to give me a b to the 4th outside, right? Because 8 divided by 2 is going to be b to the 4th. And then I'm going to have what? The square root of 3c left inside. Okay? See what's going on there? All right. Take a look at this one. The 5th root of 64, x to the 12th, y to the 8th. Okay. 64 is 8 times 8, which is 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6th power. But my index is a 5, so I'm going to think of it as 2 to the 5th times 2 to the 1, or just 2 to the 5th times 2. Okay? X to the 12th. Well, 5 doesn't go into 12 evenly, but 5 goes into 10 evenly. So I'm going to rewrite x to the 12th as x to the 10th times x squared. Okay? 5 doesn't go into 8 evenly, so I'm going to write it as x or y to the 5th times y cubed. So I've got exponents that match the index, or they're multiples of the index, or they're not going anywhere. Okay? This is going to give me a 2 outside. This is stuck inside. This is going to give me an x squared, 10 divided by 5, outside. This is stuck inside. This is going to give me a y to the 1 power outside. This is stuck inside. So inside I've got the 5th root of 2x squared y cubed. So my final answer, 2x squared y, 5th roots of 2x squared y cubed. So we take the factors inside and we write them as a power that matches the index or a multiple of the index, and then leftovers. The leftovers are going to be stuck inside. Okay. Are you familiar with Paul McCartney's song, Band on the Run? Stuck inside forever, no one seeing no one, nice again. That's those radicals. They're stuck inside forever. Thank you, Paul. Okay. So let's take a look at this one. Simplify each radical expression. All variables represent positive real numbers. So basically the same directions as before. I have the square root of 363. So what I want to do is I want to find any perfect square factors. So let's take 363 and let's factor it. 3 times 121. 3 times 11 times 11. Oh, 3 times 11 squared. Now, it might take you longer to do that than it did me. That's fine. I've been doing this for 100 years. So that's why I'm old and crusty. Okay, so now I've got that. I've got squares and leftovers. That's the leftover. The square root of 11 squared is 11 outside, so I get 11 square roots of 3. Okay. Let's see how we're doing. We've got the square root of 147, a to the 5th. 147. I don't know if you remember, but there's a rule when you're doing prime factoring. If the number's even, 2 is going to go into it. If the number ends in 0 or 5, 5 will go into it. But there's a special one involving 3s. If you add up all the digits and the sum of the digits, I can't talk at all. The sum of the digits is divisible by 3, then the original number is divisible by 3. So that means 3 goes into it, what, 49 times. So 3 times 7 times 7. So I could write this as 3 times 7 squared times a to the 4th times a. Again, I'm taking a to the 5th and pulling out powers that are multiples of 2 and then leftovers. Okay, is that making sense? Why I'm doing that? Okay, so the square root of 7 squared is 7 on the outside. The square root of a to the 4th is a squared on the outside, and I have 3a on the inside. So 7a squared square roots of 3a would be the final answer, okay? Because your leftovers stay inside. Okay, let's see. One more of these, and then we're going to look at a second rule. The cube root of 280, a to the 5th, b to the 6th. 280 is 28 times 10, is 2 times 14 times 2 times 5, is 2 times 2 times 7 times 2 times 5, is 2 cubed times 5 times 7. So there's the prime factorization of 280. Oh, I've got a cube and leftovers. So 2 cubed times 5 times 7. A to the 5th is going to become a cube and leftovers. B to the 6th, 6 is a multiple of 3, so it's going to come out nicely like it is. Okay? So I've got cubes or exponents that are multiples of the index and leftovers. Let's see. This and this and this are all going to be leftovers, aren't they? The cube root of 2 cubed is 2 outside. The cube root of a cubed is a outside. The cube root of b to the 6th is b squared outside. And then I've got the cube root of 5 times 7, 35, a squared. And typically we take the numbers inside and multiply them back together rather than write 5 times 7 times a squared inside, we write 35 a squared. Okay. All right. Second rule that we already know, but in a different form. A quotient raised to a power, you attach the outside exponent to both the numerator and the denominator. So if I had a over b to the 1 over n power, that would be a to the 1 over n all over b to the 1 over n. But if I rewrite this in radical notation, that would be the nth root of the quotient a over b is the nth root of a over the nth root of b. Again, we actually used this rule earlier back in 9.1 or 9.2, but I just kind of glossed over it and said, well, we can take this and write it. Like if I've got the square root of 4/9 That's the square root of 4 over the square root of 9, which is 2/3. And I did that without explaining it. I just did it, knowing that this was coming. So here's why I can do that, why I can split that apart. Okay. Likewise, I can go the other direction. So if I have the square root of 4 over the square root of 9, I could write that as the square root of 4/9 if I wanted to. And we'll see some reasons for doing that here shortly. Okay. We good to go on? So let's say I've got the square root of 3/4. That's the square root of 3 over the square root of 4, which is the square root of 3 over 2. Let's say I've got the 5th root of 2 over 243. Well, that's the 5th root of 2 over the 5th root of 243. But 243 is 3 times 81, which is 3 times 9 times 9, which is 3 times 3 times 3 times 3 times 3, or 3 to the 5th power. So this becomes the 5th root of 2 over the 5th root of 3 to the 5th power, which is the 5th root of 2 over 3, because the 5th root of 3 to the 5th is 3. All right. I'm sorry, am I getting too excited? I'll try and mellow out here. Okay. Now, what if you got something like this, though? You've got the square root of 128 over the square root of 2. Since the indexes, or is it indices? I'm not sure what the plural of index is, but since they're the same, I could write it like that. But then I could take what's inside and reduce it down to that and get that answer. Okay. Now, there's another way to go, and I'll show it to you only to show you that you don't want to do it that way. Okay. We could do it this way. We could say that is equal to, well, let's see, 128 is 2 times 64. So this would be the square root of 2 times 64, which would be the square root of 2 times the square root of 64 over the square root of 2. I could come in and reduce those out, but that's, you don't want to do that. That's too much work, right? But there will still be people that'll do it that way. And there's nothing wrong with it. It's not wrong, it's just long. Kind of like my explanations. Hopefully they're not wrong, but they're usually long. Okay. How about this one? The cube root of 64 y to the 8th divided by the cube root of 8y squared. That would be the cube root of 64y to the 8th over 8y squared. But that would be the cube root of 8y to the 6th. And 8 is 2 cubed, so we'd get a 2y squared. Now, what if these don't have the same index? Then you're probably in college math 141 and you're in the wrong class here or something. But in other words, we don't do that to you here. Okay. Now, it says simplify by combining like radicals. What are like radicals? Well, first of all, let's go back to what are like terms. What's 2x plus 3x? That's 5x, right? Those are like terms. They have different coefficients, but the same variable. But if I have 2x plus 3y, those are not like terms. I can't do anything with it, right? Okay, what if I had 2 square roots of 3 plus 3 square roots of 3? We say those are like radicals. The radical parts of each term are the same. So 2 of something plus 3 of something would be 5 of something, the something being the square root of 3. Okay with that? All right, so let's say we have 11 square roots of 3 plus 2 square roots of 3. That would be 13 square roots of 3. I still can't talk. What if we had 30 cube roots of 6 minus 10 cube roots of 6? Well, that would be 20 cube roots of 6, adding or subtracting like radicals. Okay, now What if we got something like this? 9 plus the square root of 45 plus the square root of 20 plus 16. Well, these look the same. That's what, 25, but these two radicals don't look to be like radicals yet. We're going to simplify each radical and then see what happens. So let's take 45. That's 9 times 5. And 20 would be 4 times 5. Okay, so what have I done? I've broken it apart into a square times 5, a square times 5. So this is 25 plus the square root of 9 is 3. The 5 stays inside. The square root of 4 is 2. The 5 stays inside. Oh, now they're like radicals. So I've got 25 plus 5 square roots of 5. And those two aren't alike, so I can't put those together. So the key here is simplify each separate term that contains a radical to see if they are like radicals or not, okay? Let's take a look at this one. The square root of 20 plus the square root of 125 minus the square root of 80. Well, 20 could be written as a square times 5. 125 could be written as a square times 5. And 80 could be written as a square times 5. Now, I kind of jumped over the process. Do you want me to go back and okay, you're okay with how I got that? All right. So this is going to be 2 square roots of 5 plus 5 square roots of 5 minus 4 square roots of 5. They're like terms. 2 plus 5 is 7 minus 4 is 3 square roots of 5. Final answer. So again, the key is to simplify each radical term first. Now, let's see here. I've got the square root of 18t plus the square root of 300t minus the square root of 243t. Well, 18 is 9 times 2, 9 being a perfect square. 300 is 100 times 3, 100 being a perfect square. 243, I think that's 3 times 81, 81 being a perfect square. Yeah, okay. And again, I kind of skipped over how I got there, but so I've got squares and leftovers, right? Okay. The square root of 9 is 3, so I've got 3 square roots of 2t plus the square root of 100 is 10 square roots of 3t minus the square root of 81, 9 square roots of 3t. Ah, they aren't all like terms though, are they? These are alike, but this one isn't the same as those. It doesn't have 3t inside, it has 2t inside. So I'm going to get 3 square roots of 2t plus what, 9 minus, or 10 minus 9 is 1, 1 square root of 3t, and I don't really need to put that 1 there. So there's, oops, there's your final answer. All righty. Well, that's all I have to torment you with today. So section 9.3, I will be back this afternoon at 1:15 with an office hour, should you decide to grace me with your presence. Otherwise, have a great rest of the day. I'm going to go ahead and stop the recording. Maybe.